Hello, everyone. This is the 2020 AB1 practice FRQ question that the Mr. Brilliant Bryan Passwater has put out there. It's a video solutions basically to all the parts of this question. Okay, so I'm going to go through there, and for the sake of time, I have inputted some information vital to each and every question, just so that the video can be, a little bit more brief. Okay, so let's go ahead and begin. The question asks, the graph of f of x is given above on the interval from -1 all the way to 11. Okay, so we know where it's defined, from here to here. The area is bounded by the graph of f of x and the x-axis on the intervals -1 to 2. Okay, that's this one here, and then 2 to 6, and then 6 to 10, and are 4, 3, and 2 respectively. So we keep reading and we see that it says given in the piecewise function defined above. So the function g of x, okay, so now a third function, is now defined by this following integral. Okay, I see x and I see t. And chances are we are going to use second fundamental theorem of calculus in order to obtain g prime is f of x, g double prime is f prime of x. Okay, so already that's where my mind is kind of going. So now that I've kind of highlighted all the parts that are kind of standing out and getting you, the reader's attention, let's go ahead and go to part A. Part A says, show that h of x is continuous at x is equal to -1. So h of x already, I'm thinking about this piecewise function that I was given. The at value is at x is equal to -1. And that means where it's actually defined. So because it's equal to -1 right here on this second function, I'm really going to concentrate at saying g of -1. Okay, so that's what I'm looking at as far as whenever I'm going to go through these 3 steps. Okay, so the 3 steps for continuity, 3 rules, if you will. H of -1 is defined is number 1. The limit as x approaches -1 of h of x exists. And then finally, the limit is equal to h of -1. Okay, so let's go ahead and go through this through the steps. Okay, so we have to say h of -1 is defined. Okay, so h of -1, if I go over here at -1 where it's equal to, what I'm really looking at is what is g of -1. That's what I'm looking at. Okay. So if g of -1 is using this function here, okay, this integral here, g of -1 is going to be equivalent to the integral from 2 to -1 of f of t in respect to t. And we would look at the graph for this instance. It's the area between the graph and the x-axis between 2 and -1. Now you can read this 2 different ways. You can read this starting from 2 and going backwards, which means that it's going to yield a negative answer of some kind. Or you can just go ahead and use a law of limits, law of integration, one of the integration laws, and change the limits of integration by flipping them over. So the -1 goes on the bottom, 2 goes up top, and we account for this law by making this negative. And now we can just interpret it as left to right with that negative constant multiple rule out in front, multiplying the whole thing. Okay, so this is saying from -1 to 2, what is the area underneath the graph of f of x? Okay, so in this case, we're going to look at the f function. We're going to go from -1 to 2, okay, and we want to find this area here. Well, this area is given to us as +4 because it's above the x-axis. So that would be +4. But because we used a law of integration and we flip the bounds, it's going to actually be a -4. So h of -1 is defined, and it's equal to, I'll write it over here, h of -1 is equal to -4. Okay, let's go to the second step. We're looking to see if the limit exists on h as far as a general limit. So we need to look at 2 one-sided limits. I need to look at the limit of h of x as I approach -1 from the left, and I also need to look at the limit of h of x as I approach -1 from the right. Okay, so let's go ahead and go to our piecewise function. And we're going to do this one first. We're going to approach -1 from the left. So if you're approaching -1 from the left, that means you're even lower than -1. So we will use this interval here. Okay, so and if I plug in -1 into x here and here, well, -1 squared is going to become a +1. Then -3 is a -2. And then -2 more is a -4. Okay, now if I use the other one-sided limit of approaching -1 from the right, I'm now going to use this interval because that's from -1 to 11. So I'm approaching -1 from the right. Therefore, it would be equal to g of -1. Okay, so g of -1 we already found from this step here. Okay, g of -1 was equivalent to h of -1, which end up becoming a -4. So we get -4. Okay, notice how here our one-sided limits, the one from the left, the one approaching from the right, they are equal to one another. Therefore, the general limit exists. This general limit exists, and it's actually -4. So far, as far as what we've shown is that it's continuous. Basically, it's defined at -1, and the value was -4, and also the limit exists, and its value is -4. Therefore, Rule 3, where the limit is equal to that defined value, also holds true, and because all three hold true, it would be continuous at -1. Okay, so that was part A. Now let's go ahead and move on. Let me unhighlight a couple of things. And we're going to go to part B. Part B says, order the values. So let me erase this so you can read it. Order the values of h double prime at -2, h double prime at +2, and h double prime at 10. And we want to go least to greatest, or smallest to the largest number. Okay, so if we're looking at h double primes, remember the functions that we were given. We were given f of x, we were given h of x, and we were given g of x. Okay, and we're trying to find h double prime at -2. So I need to first locate an h double prime graph, which would be right here. And all I did was create two piecewise functions by deriving it to get f prime, or sorry, h prime, and deriving that one to get h double prime. Okay, so if I'm looking for h double prime at -2, I need to find what domain interval am I talking about. So it's going to be in the top function. So we're going to go ahead and write h double prime at -2 is going to equal 2. It's going to equal this value that it gave as far as an output value. Okay, so now let's look for h double prime at 2. So h double prime at 2, we're going to use this same piecewise function, but this time, okay, so this same piecewise function, but this time we're looking at a value at 2. Well, that holds in this domain interval. So we're going to insert this 2 everywhere where our variables are waiting. Therefore, h double prime at 2 is the same as g double prime at 2. Okay, and g double prime at 2, if I go to this function given here as g of x, per second fundamental theorem, just like what we thought would happen, this g of x became g prime of x here, which is f of x, and then g prime of x, if we derive that, it would become g double prime right here, as far as equaling f prime of x. So h double prime is the same as g double prime of 2. Therefore, because of second fundamental theorem here, we're going to say this is also equivalent to f prime at 2. Okay, and now we have something that we can look at as far as what is the slope. Okay, so what is the slope at 2? Well, if we're given an f of x graph, we want to know what is the tangent at x is equal to 2. So if I were to draw a small little tangent here, we see that it has some negative magnitude of some sort. It looks like it's -20, maybe -10, depending on your perspective, but it is negative nonetheless. Okay, so we'll just go ahead and put that this is going to be a negative number. Okay, and then last but not least, let's go ahead and go to which one is h, or what is the value for h double prime at 10. Okay, so let's go ahead and go through our steps again. We're going to use the h double prime. Because it's at 10, we know it lies in this second interval here between -1 and 11. So this is the same as looking for g double prime at 10. Okay, and just like we did before when we were using second fundamental theorem, we know per second fundamental theorem that g double prime is the same as f prime of x, otherwise f prime at 10. So if we want to know what is the slope at 10, we go to the graph of f of x, we find this tangent at 10, and we see that this is a local minimum. And this is going to be the horizontal tangent of 0. So f prime at 10 is equal to 0. Okay, so we have three values here that we just found. We found 2, we found a negative, and we found 0. So if I'm doing it from smallest to largest, or least to greatest, I'm going to go ahead and write them out as the lowest was the negative. So we'll say f prime, whoops, not f prime. We'll say h prime at 2 was the least. And then it just kept going up from there. So we're going to say is less than our next value. So our next value is equal to 0. And that was at h prime, or double prime, that is. Let me write that in. H double prime at 10. Okay. And then last but not least, this is less than our final piece that was being asked, which was h double prime at -2. Okay, so we found the values of h double prime at -2, h double prime at 2, h double prime at 10, and here's the answer as far as from least to greatest. Okay, so let's continue. And again, that was all per second fundamental theorem, and also conjunction with looking at these piecewise functions and kind of going through their progressions of finding what is h double prime. All right, so let's go to part C. Part C is saying evaluate the following limit, or state that it does not exist. Justify your answer. So we've learned our first step is direct substitution. So if we put where x belongs, if we put a 6, we'd have 6 squared, which is 36 minus 36, which is 0 in the denominator. We'd also have up here 12 minus 12, which would give you 0. E to the power of 0 is 1. And times 3 would give me 3. So we have 3 there. And then g of 6, if we put that here, we could go over here to this piecewise function that was given and evaluate what is the area between 2 and 6. Okay, between 2 and 6 is a -3 because it is below the x-axis. So we have a -3 plus this 3 down here would give me another 0 as far as an indeterminate 0 over 0 form. And that's what you see right here. Now, this does look like L'Hopital's rule. In fact, we can use L'Hopital's rule, but we do have to give a little bit of premise as far as why and how we're going to use L'Hopital's rule. Okay, so first, let's start off by mentioning that the numerator, which is g of x plus 3 times e to the power of 12 minus 2x, is continuous. We have to mention this first, okay? And we can also show with the denominator the same thing. X squared minus 36 is also continuous. And then you can go on to say, if you wanted to find the limit of the top one, you would say the limit as x approached 6, which is what you're using here, of all of this here, okay, so I'm just going to save some room, is equal to 0. And then the limit as x approaches 6 of all of this here is also equal to 0, thus validating our indeterminate form of 0 over 0. Now, we're not saying that this is equal to 0 over 0 as far as an answer. we're showing that the top numerator is continuous and equal to 0 independently from the bottom denominator is continuous and equal to 0. Thus, we're able to use this L'Hopital's rule per the indeterminate form. Okay, so L'Hopital's rule, we've learned that L'Hopital's rule is where we can take our original ratio of f of x over g of x and basically find their derivatives and see if we can then plug in our input of 6. So let's go ahead and do that now. So it will move over to the limit as x approaches 6, and we're going to take the derivative of the top, which we get g prime of x. And the derivative of this is basically the carbon copy times the natural log of the base times the derivative of the power. So it's going to be the carbon copy of 3e to the 12 minus 2x. That's a subtraction. And it's multiplied with the derivative of the power, which is negative 2. Okay? All of this is one term, one monomial combined together with that multiplication piece right there. Okay, and in the bottom is just going to simply be 2x because that's the derivative of the denominator. Okay, so let's continue and see what we have here. If I now put in this 6 everywhere where I see an x, notice that the bottom piece will become 12. And let me go ahead and write that in right now. The bottom piece will become 12. And let's see what we get for the top piece. Well, 12 minus 12 is 0. E to the 0 is 1. Times this negative 6, if you will, because 3 times negative 2 is negative 6. I'm going to be subtracting 6 there. Now I just have to find what is g prime at 6. Well, per second fundamental theorem way up here, we obtained that g prime was the same as f of x. So what g prime at 6 is equal to is the same of what is f of 6? What is the value of f at 6? And over here, per the f of x graph, we know that the value is, because this is our position function, if you will, is 0. So we're going to put 0. So therefore, I have 0 minus 6, which is negative 6 over 12, becomes negative 1/2. That would be the answer for this limit. Okay, so now let's go to part D. Let me make a little bit of room. Part D is evaluating the following integral. And this integral is pretty involved, okay? First of all, we have to see how many terms do we have. And since addition and subtraction kind of separate multiplicative monomials, we know that we have 2 terms. This tells me, okay, I'm going to be splitting this up, again, using integration laws, where the integral of this sum, okay, let me highlight that, the integral of the sum becomes the sum of the integrals. So when you break this up, we get the integral from 1 to 7 of the following, plus the integral from 1 to 7 of 5 dx. Notice that I constant multiple ruled anything out that was a constant, okay, that was multiplied in. So therefore, I'm just integrating the following of what you see. Okay, I'm just integrating this by hand from here. Okay, so let me go ahead and make some room here. I'm going to take off just this work so that we can work here and have space. And let's go ahead and do the integral in red. So I'm saying 3 times this from 1 to 7, the integral from 1 to 7 of the following function. You should notice immediately that because this is more than just one variable, like x, y, or z, or t, whatever it is, it's more than just a variable that has a positive 1 coefficient. We're going to use U-substitution of some kind. Okay, so if it said just h prime of x, we wouldn't have to use U-substitution, because if it said h prime of x, that coefficient in front of x is just positive 1. There's no composite functions needing that U-substitution. But because it's more than just x, we're going to go ahead and use U-substitution. And we're going to say, let u equal 2x minus 4. Therefore, du is going to be 2 dx. And what I'm doing right now is I'm about to rewrite this in terms of u. Okay, so this will become 1/2 du is going to be substituted where dx is at. Therefore, our new integral that becomes from this U-substitution is going to be 3/2, okay, because I'm constant multiple rule that 1/2 with a 3. And now it's going to be from different limits of integration. So 1 plugged in there would give me a -2. So that's my new limit of integration, my lower limit bound. And then whenever I plug in this 7 here, I'll get 14 minus 4, which is 10. And then now I just have to finish this up. It's going to be, remember, u was all of this, so it's going to be h prime of u. And it's going to be du. Okay? So that's how we do the u substitution, and then we're going to figure it out from here what h prime of u is equivalent to up here. With this piecewise function, what we were given before, we were given this, and we derived so we could get, again, the derivative and the acceleration piecewise function. Okay? I'm going to now evaluate the integral, or the area underneath the curve, from -2 all the way to 2. So we know the antiderivative of h prime is just h of u. Okay? And I'm evaluating this from -2 to 10. In constant multiple ruling, there's 3/2 right here that I'm going to multiply thereafter. So what this is looking for, and this is again just fundamental theorem, is h of 10 minus h of -2 is therefore then going to be multiplied with this 3/2 out in front. Okay, so we're actually going to use our given piecewise function, and we're going to evaluate what is h of 10. Okay, h of 10, well, 10 lies in this domain, so it's the same as saying what is g of 10. Okay, so g of 10 means we're going to use this second fundamental theorem problem, right? Or this equation that we were using with second fundamental theorem. And all we want to find is h, whoops, let me not erase that. H of 10 is the same as g of 10, which is the same as what is the area underneath the curve between 2 and 10. Well, between 2 and 10, I have a -3 because it's below the x-axis, and a +2. So a -3 plus that +2 is going to yield a -1. So this is -1. A lot going on there. If you have to rewind, please do so. And pause and whatever you need to. So the other one is, what is h of -2? So when we come up here, we need to find out where is -2. Well, it's in this domain, okay, this interval. And we're going to plug in this -2 so that we get -2 squared is a +4 minus 6 minus 2, so that we get a -4. Okay, so right here, let's go ahead and write this out. This will give me a -4. And since we're still doing this f of b minus f of a, we'll have -1 minus a -4 is the same as adding 4, which becomes 3. And 3 times 3/2 becomes 9/2. Okay, so 9/2 is the area, or sorry, the value of this integral, this first one that we broke up. Okay, so I'm running out of room a little bit. I'm going to write over here on the bottom right-hand corner, but that's how you would get that value for the first one. The other one's a lot easier. It's just going to be the integral of this guy right here. It's from 1 to 7 dx times 5. Okay, so the integral, let's go ahead and write it. Actually, we'll make some room right here. Let me change this by kind of, no, I'll just erase and make room like that. Okay, and then let's go ahead and take the integral. And the integral of dx is just x, evaluated from 1 to 7. And then constant multiple ruled with that 5. So fundamental theorem says f of b is 7 minus f of a, which is 1. And then we're just going to constant multiple rule that with 5. So 7 minus 1 is 6, times 5 is going to be 30. So we have 30 is going to be added. So this was 30 right here. Whoops, let me use a different color. This 30 is right here, and it's going to be added with the 9/2. So you could just say 30 and 9/2, or if you wanted to get common denominators, you could say 9/2. Let's multiply by, because right now it's a denominator of 1. Let's multiply by a form of 1. So we have common denominators. We'll say 2 over 2, which will get 69 over 2. So 69 over 2 is the value of this integral in general. Okay, so now let's go to part E. It says, let y equals k of x be the particular solution for this differential equation right here. Okay, dy dx is equal to h prime of x times y minus 1 for x's that are less than negative 1. Okay, this is going to become important here in just a bit. Find the particular solution given that x initial condition is negative 2 and y value is positive 2. Okay, so let's do the separation of variables and group the y's together on the left side. And the reason why I'm moving the dx's to the right is because we cannot have dx or dy, anything that we're integrating, that in respect to variable cannot be located on the denominator. You have to have it in the numerator per se. So we would multiply to the right side and become h prime of x dx. That's our separation of variables. Okay, and now we're ready to integrate. The left side is going to become the natural log of the absolute value of y minus 1. The right side becomes, well, what is the integral of h prime of x? Now, I can go ahead and just go to h of x and then kind of find the c that way. Or I can just say, what is h prime of x? Where it's less than negative 1. Okay, h prime of x, where it's less than negative 1, is occurring here, and that is 2x plus 3. This is h prime of x, where x is less than negative 1. Where we have h prime of x is less than negative 1, we're going to write that 2x plus 3. Okay, so 2x plus 3, is still the integral that we have to take in order to get, and I should have probably written this as an intermittent or intermediate kind of work, if you will, so that the integral would become x squared over 2, so it becomes x squared plus 3x plus c. Okay, so now we're going to use our initial condition of negative 2 where we see an x, and we're going to use this positive 2 where we see a y. So that the left side becomes the natural log of 1, which is just 0. And that the right side, let me show that, the right side would become, we'll plug in negative 2 where x is at. So we have 4 minus 6, this is a negative 2 plus c. Therefore, when I move it over, c is going to become a positive 2. Okay, so back here, this was my general solution because we didn't know our c, our constant term. So this is our general solution. It's still variegated because we don't know c yet. But now that we've found it, we can upgrade it to the particular solution. Okay, so the particular solution will have this c is equal to 2. So we'll have the natural log of the absolute value of y minus 1 is equal to x squared plus 3x plus 2. And now, to solve my answer, we just got to get y by itself. So let's apply base e to both sides. Okay, so this would cancel this out where we have y minus 1, and we would have e to the power of all of this function here. And then this is a positive or a negative form from here. So if I take off the absolute value from both sides, we know that it could be a positive or negative version of all of this. Okay, we'll decide that here in just a bit. And last but not least, we're going to move this 1 over to the right by adding it. Okay, so let's go ahead and add that 1 over here. So to test this, we can use our negative 2. Let me show you our negative 2 input right here that was given everywhere where x is at. So again, we would have negative 2 raised to the power of 2 is 4, minus 6 is negative 2, plus this 2 is a 0, so e to the 0 is 1. So 1 plus 1 would then get us to this output value of 2. And the only way that'll work is we have to decide between the positive and negative here, and that came from that absolute value piece when we removed it. In this case, it's going to become the positive because it has to be a positive 1 adding with this 1 here in order to yield this positive 2. Okay, so we would have a positive E. So our final answer becomes y of x, or you can even say y or k of x, is equal to e to the power of x squared plus 3x plus 2, and on the bottom, plus 1. That would be the answer to part E.